Good morning. We have been dealing with the various hydraulic structures in the irrigation management of water to the agricultural lands. So we have seen yesterday the canal regulator, day before yesterday. Yesterday we have seen aqueduct. Usually a canal regulator and aqueduct, the proximity will be very high, because suppose you want to do some repair work on the aqueduct, and if the canal is running full, you want to close the shutter and do the repair work. So if a road crosses a canal and if a nearby a river is there, the canal regulator will be at the upstream side. After canal regulator, you will see the aqueduct. Then we have seen big dams. We have seen check dam. I told you the check dam also. These weirs, there are different types of weirs known as surplus weir. One type of is surplus weir. Surplus weir means whenever you have more water, that will overflow. Surplus weir. Another is vertical drop weir. Another is vertical drop weir. Then surplus escape. Surplus escape. Then flush escape. These are four types of facilitating water flow upstream of these structures and downstream of these structures. Surplus weir, all will be across the river, a water stream. Check dam also can be included in the case of a weir. They will have a body wall, basically as you have seen the canal drop. You will have a body wall, usually trapezoidal in shape. Sometimes there will be a projection to keep little more water at the upstream, known as the dam stones. You have dam stones with the grooves on which you will put a shutter-like things, usually 50 to 75 centimeters more above the body of the dam. Weir. So this weir will have a foundation and all water retaining structures. As you have seen, the abutment, wing wall, and the return, there are mandatory structures beneath the ground, beneath the soil, in all the cases. We kept that now because after telling all these hydraulic structures, wherever you have a water retaining structure, water controlling structure, the body of the controlling structure will have a suitable foundation, and this foundation will be extending to the downstream and the upstream. They are called the aprons. Aprons. So you will have the bottom of the soil, bed of the water stream, you will have a thick masonry or stone or even concrete structure extending lengthwise towards a considerable length at the upstream of the weir as well as at the downstream of the weir. Usually the downstream portion will have more length. Downstream portion will have more length because the load coming from the downstream side on the apron will be less. Whereas in the upstream side you have water, inbounding water load will be more. So usually the downstream side aprons will have more length. The purpose of this apron, impermeable aprons, then there will be some part which are permeable. First impermeable, continuous to the body of the weir. Below that, the strong foundation. The foundation will be extended as wings upstream apron and downstream apron. Usually the upstream aprons have to be thicker because they have to resist water load and the uplift pressure. Because uplift pressure will be maximum at the upstream side. So to take care of the upstream pressure and the water load, you will have upstream aprons thicker and downstream aprons not that much thicker. And usually the downstream length of the aprons will be more compared to the upstream. I hope that you know where the position of the apron is. It's just below the body of the dam, underneath the soil, extending from the foundation on either side of the aprons. The purpose of these aprons are, when water comes, I told you, it percolates into, then it horizontally moves, which is known as the creep. So it horizontally moves through the pores and the joints, then it comes up at the downstream where you have an opening. I mean, it comes out, seeps out. This is the uplift pressure. At the same time, when water comes like this, you have a head causing this flow. Head is nothing but the water level at the upstream side of the structure. That water and the length, this length of flow, the horizontal length of flow is known as the gradient, H by L. Head divided by length of creep. Head divided by length of creep is called the gradient. And when it comes, gradient gradually reduces because L increases to the downstream side. So H by L at the upstream side will be more. H by L at the downstream end will be less because the denominator is more, because the length of the apron is more. Then the last point from where the water seeps up, comes out, is called exit gradient. That gradient is called the exit gradient. Exit gradient is nothing but the head causing flow divided by the maximum length of the apron, upstream plus downstream. When this exit gradient is more than the hydraulic gradient, you have an existing hydraulic gradient at the surface. The water is, I have showed you upstream water and then downstream tail water race. So there is a difference H1 and H2, tail water race and upstream water. So H1 minus H2 is the head. That divided by L, we have a hydraulic gradient at that point. From the, considering the surface, there will be a hydraulic gradient. Considering this, you have an exit gradient. When this exit gradient is more than the hydraulic gradient, when the exit gradient is more than the hydraulic gradient, not only water will come out, along with that, the soil particles also will come out. So,
a dam is a barrier that restricts the flow of water and can be used to collect the water. This water may be utilized for many purposes such as irrigation, human consumption, industrial use and hydropower generation. Many times these dams or such hydraulic structures are built on pervious foundation and water flows through the voids present in the soil from high hydraulic head to low hydraulic head. This phenomenon of water, movement of water through the soil is called seepage. As the water flows through the soil, the water exerts a drag on the soil particles in the direction of its motion. This force applied by the water on the soil particles is called seepage force. And because of it, pressure developed in the soil is termed as seepage pressure. When water flows in the soil in horizontal direction, it exerts seepage force on the particles in the horizontal direction. And when it flows vertically, the force is exerted in vertical direction. If this exerted force is strong, it has the capability to displace the soil particles in its way, and particles may get carried away by the flowing water. This phenomena leads to a very serious problem in the soil engineering, development of channels in the soil. And this phenomena is called piping. When water flows through the pervious foundation of any dam with a very high hydraulic gradient, it may carry soil particles with it, causing to form pipe-shaped channels in its foundation. And the structure may fail because of piping failure. There are two types of piping failures: backward erosion piping failure and heave piping failure. Let's begin with backward erosion piping failure. When water percolates through the soil under any hydraulic structure, it may happen to exit vertically upwards at the downstream. If this water moves with a high hydraulic gradient, the seepage force or drag exerted by it on the soil particles may push them up, and the soil particles at the exit point of the water may be removed by the force of water. This removal of soil particles decreases the length of flow, and that increases the hydraulic gradient even more, causing further removal of the soil. This process of erosion of soil in the backward direction continues towards the upstream, and a pipe-like opening is formed below the dam. Hydraulic structure becomes unstable and may fail. This type of piping is called backward erosion piping. Generally, backward erosion piping failure occurs when the exit gradient becomes greater than the critical hydraulic gradient. The hydraulic gradient near the exit point of the water is called exit gradient. If we draw the flow net for this particular flow condition, we may calculate the exit gradient as the drop of head through the last flow field divided by the length of the flow field. Critical hydraulic gradient is the hydraulic gradient with which, when water flows in the soil in upward direction, the seepage force or drag exerted by water on soil particles, which pushes them up, completely balances the weight of these particles, and they seem to be suspended in the water. Soil in such state does not behave like a soil anymore, but behaves like a viscous liquid. Soil loses all its shear strength and is no longer able to support any load. For the safety of the structure, the exit gradient must be very low from the critical hydraulic gradient. This piping phenomena leads to the whole structure failure, and it is so serious that for safety against piping, a factor of safety of at least 6 is recommended. If the dam that holds the water is an earth dam, that is, it is made up of earth material such as rocks and soil, this backward erosion piping may also occur in the body of the structure. Then the second piping failure is heave piping failure. Heave meaning is to lift or raise something with a great force. This kind of failure may also occur on the downstream side of a hydraulic structure when the water is coming out vertically upwards. It occurs when the upward seepage force acting on the particles over an area exceeds the downward force because of the submerged weight of the soil above that area. This condition destabilizes the soil, and if this uplift force acts opposite to the force of gravity due to the weight of the dam, and if it is high enough, it may destabilize the whole structure. To prevent backward erosion piping or heave piping failure, the upward seepage force exerted by the water on the soil particles should be less than the downward force due to the weight of the soil or structure or any other arrangement. So, factor of safety against the piping in the soil can be written as the weight of everything above, which is downward force divided by the upward seepage force applied by the water. If value of downward force, that is weight of overlying material, is twice the value of the upward force, we receive the factor of safety as 2. This means the structure is twice safe. Downward force is greater than uplift force, so the structure is safe and is twice strong. There are few methods through which we can prevent the piping failure. First is increasing the path of flow. We know The hydraulic gradient is the head loss over the length of flow. We can see in this situation, it is difficult to decrease the head loss, but we have control over the length of the flow over which it is percolating. If we increase the length of the flow, the hydraulic gradient will decrease, and that also cause to decrease the exit gradient. We can increase the length of the flow so that exit gradient becomes well below the critical hydraulic gradient and the structure will be safe. There are a few methods through which we can increase this flow path. First, we can increase the base width of the hydraulic structure, so water has to travel more to reach the downstream and length of the flow is increased. Second, we can provide vertical cutoff walls below the structure at upstream end. Thereby, water has to go below this wall to reach the downstream. Third, we can also provide an impervious blanket on the upstream. Second method to prevent the piping failure is reducing seepage. If our hydraulic structure is an earth dam, we can reduce possibility of piping failure through the body of the dam by the reduction of seepage through its body. For that, we provide an impervious core through which water cannot flow. We can also provide the drainage filter near the top of the earth dam. Drainage filter consists of layers of pervious material which permits flow of water but prevent the movement of soil particles. Drainage filter changes the direction of the flow away from the downstream face and avoid piping through the body of the dam. Then, to prevent the piping failure, we may provide a loaded filter. It is provided at the downstream from where the water emerges out. A loaded filter consists of pervious material such as graded sand and gravels. The loaded filter increases the downward force to counter the upward seepage force at the point where water emerges out from the soil. Hence, the loaded filter increases the factor of safety against piping. And the factor of safety is given as a weight of soil plus weight of filter divided by the upward seepage force. Filters are so designed that they are more permeable than the soil they protect, and yet their particles are not very big that the fine particles of the soil they protect can move through the voids in the filter. If you like elementary engineering videos, you may support it on Patreon, or you may buy Elementary Engineering's handmade diaries at Professor. Read Piping Failure on elementaryengineeringlibrary.com. All the links are in the description. Thank you.
From the horizontal creep, the water creeps along with taking materials also when this exit gradient is more than the hydraulic. So after some time you will see a cavity, literal cavity between the foundation and the soil strata. That is known as piping or quicksand. That is known as piping or quicksand. Suppose you allow that piping, whole structure will sink. That is a disaster. So we should never allow piping to take place. Piping is a phenomenon where the soil particles also will be carried along with the creeping water because the exit gradient is more than the hydraulic. So it is the art of the structural engineer or hydraulic engineer to see that the creep length is maximum, by which always the exit gradient is kept limited, always well within the hydraulic gradient. That is possible. You will try with the horizontal length, increasing the downstream apron, keeping the required upstream apron. Even after that, you cannot go on doing it. Suppose you cannot do it, what you will do is, you will pile upstream piles and intermittent piles. So what will happen? Water comes, the pile doesn't allow the water to go straight, So water has to creep along the vertical line, then go along the white line. So staggering. I hope you got. If you have a series of piles, especially at the upstream side, obviously the length of creep will increase. The total length of creep will increase because it has to take the vertical direction, go up, again take a horizontal distance, vertical goes. So the total creep length increases, by which the denominator increases. So the exit gradient will be well within the hydraulic. So piping will not increase. Those piles are called sheet piles. So the one purpose of the sheet pipe is to resist the upward load. Resist the not resist the upward load, resist the load overburden, superstructure load. Sheet piles will take. Piles are deep structural elements. There are timber piles, there are concrete piles, there are pre-stressed piles. You can have cast in situ pre-stressed piles, or you can have precast piles. There can be group of piles having a cap resisting the load. Here it is sheet pile, so it will have a width also, usually steel sheets, plates. Then only at least the sheet piles have to extend to the length of the body of the weir. Otherwise, water will go up the other side. So to completely arrest the horizontal flow directly, you need a plate-like structure. That plate-like structure extending well below the soil to a great extent is known as sheet piles. They are vertically mounted. The purpose of the sheet piles is to arrest the direct flow in the horizontal direction, arrest the creep, then take a vertical direction downwards and upwards. You will have usually one upstream sheet piles. Upstream sheet pile will be there. You can have intermittent sheet piles too, to take care of quicksand or piping. Piping is a very great defect. If it takes place, it will affect the stability and structure, safety of the dam. So piping shall not happen. So sheet piles to a great extent will take care of piping. So this completes almost our hydraulic structures. Usually while we are dealing in irrigation engineering, hydraulic structures will be dealt later after telling about the process of irrigation. That is a usual method. First you have to highlight irrigation, what is irrigation, what is the purpose. Then you have to explain hydraulic structures. I just tried a reverse order because once you know the components, these hydraulic structures, their role in facilitating water flow, controlling water flow, retaining water flow, accumulating water flow, maintaining water level, and controlling the quantity of water with a required velocity, one can appreciate the amount of involvement these structures have in having a very effective, efficient irrigation system. So, these hydraulic structures are the cause for a well-managed irrigation system with the available water which is stored during heavy rain and distributed according to the requirement of the crop, according to the season of the crop, especially in the case of a direct irrigation system. And the last hydraulic structure is in the field channel or the canal, which is known as the canal outlets. Canal outlets are module. Outlets are module. Canal outlets or modules are nothing but the hydraulic structures or irrigation structures allowing definite amount of water to the farmers. So usually they will be connecting the branch canal and the field channel. So how much water is required for a particular agricultural field for the particular crop, that water will be monitored. The quantity of water can be managed by canal outlet works. There are two types of outlet works. One is the flexible outlet, another is the rigid outlet. The difference between the flexible outlet and the rigid outlet. One example of flexible outlet is Kennedy's outlet. Kennedy's outlet, and the ridge outlet is Gibbs outlet. Gibbs module. In the Kennedy's outlet, the farmer can manipulate the flow of water. Flexible outlet, you can adjust the quantity of water to the agriculture land. It's flexible. In a rigid module, in a Gibbs module or Gibbs outlet, the quantity is rigid, fixed. Farmers cannot tamper with the quantity of water to their agriculture land. So that completes the hydraulic sections. By God's case, we will try to wind up irrigation tomorrow by telling water requirements of crop and other things tomorrow. Thank you very much. God bless.